Okay, so I have started the recording, so let's get started. So, hello and welcome everyone. Today we have Pallavi from IIT Madras, and she will be talking about her recent work that appeared at Using Security. I guess she presented it at Using Security just last month. It's a pretty freshly baked work. Looking forward to more insights. Pallavi, over to you.
Thank you, Professor. Hello everyone. As Professor mentioned, I'm Pallavi. I'm from I2SSL Labs, a CYSEC group at IIT Madras. And today I'll be talking about our work in collaboration with TAMU and TU Darmstadt, named WhisperFuzz, white box fuzzing for detecting and locating timing vulnerabilities in processor. So let's begin. Hardware vulnerabilities are a critical concern for all the commercial and open source processor designs which are available today. These vulnerabilities allow for unprivileged access to sensitive data. They can compromise the entire system and they risk the privacy and the security of users. Existing solutions for combating these vulnerabilities suffer from two major limitations. These solutions do not offer any root cause localization. For mitigation, first, the source of any detected vulnerability has to be located. And current solutions, they require manual effort for such localization. That introduces inefficiency and also manual error. The second limitation is also that these solutions use irrelevant coverage metrics. These metrics do not allow for an accurate estimation of the achieved security of the processor against the concerned vulnerability. Hence, we propose our solution, WhisperFuzz, which overcomes both of these limitations. It is completely automated, it performs root cause localization, and it also provides an effective coverage metric for the vulnerability that we target. So, what is the vulnerability that we target? We target timing vulnerabilities in processors. Timing vulnerabilities pose a critical and a pervasive threat to virtually every processor in use today. These vulnerabilities are not just theoretical, they have been repeatedly demonstrated to severely compromise user privacy, leak highly sensitive and confidential data, and even extract intricate details of proprietary tools. The widespread nature of these vulnerabilities underscores the urgent and the far reaching implications for security across all the platforms. So, let us take a look at what these timing vulnerabilities actually are and how they work. Any processor, when given an input, takes a certain amount of execution time to generate an output. If this time is dependent upon some confidential information, if we vary the information, it results in an observable difference in the execution time. This difference can then be used to extract information, this confidential information. For example, let us consider a processor with a shared LLC between multiple threads. One such thread is a victim thread, which which accesses an address based on some secret information, and another thread is controlled by an attacker. Now, the attacker wants to extract the secret information, and hence the attacker performs what is known as a prime and probe timing attack. In the prime phase, the attacker selects a cache, let's say set 1, and fills this set with cache lines from their own memory. The attacker then waits for a fixed time interval. In this interval, the victim accesses a line from some set, let's say X. After the fixed interval, the attacker then again accesses all the lines that they have placed in the cache set 1. This phase of the attack is known as the probe phase. So what happens is that if the victim placed a line in the same cache set, that is cache set 1 is the attacker, it would have evicted at least one of the attacker's lines. And when in the probe phase, the attacker tries a timed access of the attacker's memory from the set 1, the attacker will observe a higher execution time and will infer that it has been a cache miss. On the other hand, if the line accessed by the victim does not lie in set 1, the attacker observes a lower execution time and hence the attacker infers a cache hit. This time difference between servicing a cache hit and a cache miss actually informs the attacker the set address of the line accessed by the victim. Since this address was dependent upon a secret in the victim's program, the attacker is able to expose the secret. So this is a sample timing side channel attack on the cache. Does that mean that timing attacks are only able to target the cache? That would mean that we can just protect the cache and our work is done, right? No, that is not actually the case. Timing vulnerabilities have been shown to originate from various sources in the processor, including the cache, the ALU, your crypto cores, different buffers, and so on. Each source has been practically shown across the industry as well as the academia to cause a lot of devastating results. In each of the modules, the cause of this vulnerability differs. In the cache, the vulnerability arises from the time difference in servicing a cache hit and a cache miss. This vulnerability has been exploited through various attacks such as Spectre and Meltdown. In the ALU, it arises from operations which differ in execution time dependent on the data given to these operations. We shall see various examples of the vulnerability affecting the ALU in towards the end of our talk. In the crypto cores, the timing vulnerability arises due to the implementation itself operating in variable time, and this has been shown to affect some RSA implementations. Timing vulnerabilities also impact various buffers in the processor, such as like the load store buffers, by exploiting contention to expose the details regarding the stored information. All of these vulnerabilities can be exploited to extract information which is either executing or is stored in the respective module that it is targeting. Over the years, these attacks have been evolving to become more powerful and complex. Since their discovery in 1996, older trends in the timing channels actually focused on exploiting differences occurring due to inherent behaviors, such as the cache hit and miss, which is exploited by the prime and probe, as we saw. However, recent trends in timing channels tend toward exploiting speculation in modern processors, making these attacks more sophisticated and critical, while also making the mitigations more expensive. Hence, it is essential to detect such vulnerabilities within the processor design before it is actually fabricated to ensure the security of the data. Existing works for such timing vulnerability detection can actually be divided into four major categories according to the method used. These categories include formal verification, static analysis, template based, and also runtime detection. However, these methods suffer from various limitations, the most critical of which are the requirement of significant manual effort and the inability of these methods to scale to larger processors due to state explosion. However, hardware fuzzing has been shown to be a promising approach that combats these and can be actually made scalable and is by design automated. So, does that mean that detection strategies using hardware fuzzing don't exist? Of course they do. But these are like just a small subset of the existing detection methods using hardware fuzzing. Then does that mean that our problem is solved? No. All of these methods suffer from three common limitations. We have a lot of these fuzzers actually require manual effort, even though hardware fuzzing ideally should be completely automated. These methods also do not allow for any root cause localization, and they also do not provide relevant coverage. While overcoming these limitations in our work, we face various challenges, and in response, we provide these contributions. So, our first challenge was scaling to the immense size of a full-fledged processor. Hence, we completely automated our tool using hardware fuzzing. thereby providing the first automated white box puzzle. Our second challenge was to localize the root cause of the detected vulnerability. And in response, we developed a technique to graphically represent the full processor. Our third challenge was to provide a coverage metric that is relevant to the state space of timing vulnerabilities. Hence, we developed and provided such a metric. Our tool is applicable to novel vulnerabilities present within the processor, and we also evaluate it on three pipeline processors. For the rest of this talk, we shall focus on the high level idea and the details of our tool. So let's begin with like the high level idea. For a processor RTL model, consider two instruction sequences with the same instructions but differing operands. One instruction sequence takes less time to execute compared to the other sequence, thereby causing a timing difference, which can then be exploited to leak the value of the differing operand. Measuring the differing execution times corresponding to each of these sequences assists us in detecting the timing differences. Now that we can detect such timing differences, we focus on our two major objectives, which are the localization of the root cause, and the second one is a coverage analysis. So let us start with localization. To apply our tool to immensely complex processor designs, we first represent the processor as an event graph. However, for this representation of the design, our event graph should have four salient properties. It should be able to represent the complete design. And the first one is that it should be able to represent a complete design. The second one is that since we apply it to detect timing vulnerabilities, it should be able to predict the time taken for each node within the graph. The third is that it should be able to track changes in the RTL at a timing accurate level. And it should also be agnostic to the hardware language or the RTL language which is being used. So we accomplish this by developing the micro event graph. Let us take a look at this method using an example. Uh, in this code, we see a cache module which checks if a particular cache line is present. If it is not, it fetches this line through a memory called submodule. This entire RTL module can be represented using the shown micro event graph. Each RTL detail is modeled in the graph through relations in the various nodes. Hence, we achieve our first objective, our first requirement, which was to represent the complete RTL. Secondly, each node in the graph takes a fixed amount of clock cycles to execute. Hence, we can predict the time required for each node. Combined together, we can now represent our RTL, and we also have a timing accurate graph, which is completely language agnostic. So now that we have a representation of this category, how do we use it to localize the vulnerability? We make an important observation related to this micro event graph and the input instruction. Each instruction sequence follows a specific path in the graph from the input to the output. Two instruction sequences consuming different execution times will follow differing paths in the event graph. By tracing these two paths followed by the input sequences, we can therefore locate the initial event which caused the two paths to bifurcate. This event is then the source of our vulnerability. Now that we are done with localizing our vulnerability within the RTL, we move on to our next objective, which was getting a relevant coverage metric. So for getting a relevant coverage metric, we again use our micro event graph. And the metric that we use is we calculate the number of paths that our tool has been able to traverse, and we divide it by the total number of paths which are present in the complete graph. there are immense number of paths which are present in various modules in the processors because the current day processors are incredibly complex. For example, in the branch predictor module of one of the processors that we tested, we had around 470,000 paths which were present. So now that we have our various components of the tool, we go for automating our approach. For this, we need various modules. First, we need to generate a sequence of instructions. For this, we use a fuzzer. Next, from this sequence of instructions, we need to mutate the operands. For this, we use the operand mutator. Third, we need to generate the event graph from the given RTL. For this, we use the event graph extractor. The fourth module that we need is for extracting the coverage which has been achieved by the tool. And for this, we use the coverage analyzer. And the fifth module that we need is the diagnoser, which actually does the root cause localization. Put together, our framework looks like this. We have one portion which detects timing channels and another which locates timing channels. In the detection, first the fuzzer generates that instruction and gives them to the mutator. Let us take a look at this portion of it in detail. So for the detection, first the ISA of the processor, for example, if we have a RISC-V processor, the RISC-V ISA is given as an input to the fuzzer. For our tool, we just used an off-the-shelf fuzzer. This fuzzer then generates various instruction sequences. These instruction sequences are then given to an operand mutator. This operand mutator mutates all the immediate operands and addresses and so on, which are present in the instruction sequences to generate a huge range of mutated input instruction sequences. Let us just take a look at two of such sequences. These two sequences are given to a simulation. We simulate the given processor design and run these two instruction sequences on the simulation. From this, we extract the amount of execution time which has been consumed by the simulation, by the design, for running these instruction sequences. And we also extract a coverage report which is specific to our coverage metric. This coverage report is then given to the second part of our tool, which is the localization and the coverage. For first, the localization, the coverage reports are given to the diagnoser. The diagnoser also gets the complete graph which has been generated. By the combination of these, the diagnoser is able to compare the two coverage reports to get and find the particular node within the graph which has caused this bifurcation in the paths that was taken by the two sequences. The second part is our coverage. So the coverage analyzer also receives the coverage reports as well as the generated event graph, and it generates the coverage metric that was observed in this particular run of the tool. So by running the tool for multiple iterations, you can actually increase the achieved coverage by the tool. So let's move on to how we evaluate our tool. So we evaluated Whisper-Fuzz on three RISC-V processors, the CVS6, which has been used in various use cases, including self-driving cars and also some processors. We also evaluated it on Boom, which again has been used in is a high performance processor and has been used in various IoT devices. And we evaluated it on Rocket Chip, which is similarly used in IoT devices and also for edge computing. So all of these processors are high performance. They are all pipelined, open source, and also regularly updated and highly contributed and rated on GitHub. So let us take a look at, we detected 12 novel vulnerabilities in these three processors. Let us take a look at one of these vulnerabilities. The CVS6 processor actually suffers from a vulnerability, a timing vulnerability, where any compressed instructions given to it show a difference in the execution time depending upon the operand. If the operand is equal to 0 in the compressed instruction, it takes 35 clock cycles, whereas if it is not equal to 0, it takes 24 clock cycles to execute. So how can this timing difference be used to extract some confidential data? Consider there is a sample program, which is a cryptographic program, which is running on this processor. This crypto program loads a key and then moves this key value from one register to another. This move instruction is a compressed instruction which is used. So if the value of the key is equal to 0, then this instruction would take more clock cycles. Whereas if it is not equal to 0, then it would take less clock cycles. So from this difference, this difference is actually very visible when executing. So you can extract the value of this key by observing the execution of this sequence. Furthermore, our tool also extracts various coverage statistics for all the different processors that we tested. These are the coverage statistics for some of the modules in the Boom processor. The other coverage statistics for the other two processors are available in the paper if you want to take a look at it. So we we propose a method which combines information flow tracing and also fuzzing to localize timing vulnerabilities effectively. Our method provides a novel leakage coverage metric, which is particular to timing channels. We have discovered 12 new vulnerabilities, and our method is also compatible with all various hardware definition languages which are present today. That is all for the talk. Please let me know if you have any questions.
Thanks, Pallavi. Maybe before others start, I have few questions. So your evaluation is done on in-order processors, or you also tested on some of the out-of-order processors?
So one of the processors, the rocket ship was in order, and the boom is out of order. The CVS6 processor is something in the middle, so it claims to be in order, but it has an out of order execution unit.
And any specific insights keeping this dynamics of processors, or in all the machines you were able to fudge and your coverage was good enough in all these cases?
So one of the things was the coverage in case of Boom, I would say, was lesser compared to the other two processors. But I would also say that the Boom processor is an incredibly complex processor compared to the other two. So overall, it was actually compatible with the complexity of it was comparable with the complexity of the processors, the coverage.
Could you go back to previous slide number 38?
Yeah, sure.
Yeah. So could you spell out what exactly you are showing here?
So in this case, I'm showing the amount of achieved coverage. Like for example, in the IO module, IOMSHR module, our coverage exceeds 20% of the various paths which are present in the graph of this module. So from all the paths which are present in the graph, we were able to cover more than 20% of these paths in just 3 iterations of our tool.
But still, there are many paths you could not cover, right? Is that understanding
Yes.
correct?
Yes, exactly. So one of the reasons that we theorized we couldn't cover them was because our fuzzer was actually not using the coverage that we have generated as a feedback. So we generate a coverage for covering these paths, and if we are able to use this as a feedback to again use to give it to the fuzzer, we would be able to get a higher coverage in that chance, in that case. But currently, what we wanted to show was that our work was actually compatible with various off-the-shelf puzzles that anyone would want to use.
Got it. Got it. Mhm. Yeah, but there is still scope for making it better, right?
Yes, yes.
Yeah. Okay. Yeah, I'm good. Anyone
Uh,
else?
yes. Hi, Pallavi. This is Shaindeep. So I have a few questions. So first of all, one is regarding the coverage. So if I understand it correctly, you are trying to estimate the standard coverage matrices of an RTL, right? The code coverage, toggle coverage, etc., right? Or it's slightly different.
No, no, no. So in case of coverage, we have a normal coverage metric where we use the path coverage, but in this case, we are talking about paths in the micro event graph that we have developed.
Mhm.
So the micro
So
event graph actually tells you the various timing behaviors that your processor can have.
Regarding that only, so now, if I understand it correctly, you are giving the inputs from the fuzzer to the RTL code, right? And then trying to, use that so that is also giving you some coverage report, and based on that, you are trying to map that coverage report on your micro event graph to see how many paths are covered, right? Am I right on this?
No, actually, the coverage report that we are getting from there is we inject we inject the micro event graphs as a statistic into the not as a statistic as like assertions and stuff into the RTL. So that
Okay, so
report that
RTL,
we
you are
are
using
getting.
okay, so you are writing assertion in the RTL and basically trying to check the coverage from there, right?
Yes.
Okay. Yeah, so it's more like what is done in standard formal methods also, like writing assertions and checking things are working properly or not. These assertions are like some SMV assertions or something else also.
Yeah. Yeah. They're
Okay.
Verilog system Verilog assertions. Yes.
System Verilog also. Okay, fine.
SPA.
Another question is that like when you are checking all these things like graph and all, so uh, so is it, I mean, one thing I'm probably missing, like this coverage that you are getting is basically you are trying to estimate the path coverage over the entire processor, right? So why it is not possible so far, like to give a, because fuzzers, I'm not very much aware about fuzzers, but they're basically generating the outputs which you are giving as input to the RTL module, right? So why is it not possible to simply use like some kind of genetic algorithm or something to generate your code where you can use this coverage metric as your cost function? Is it difficult, too difficult, or there is some other issues?
It so it can. I am not very aware of genetic algorithms and such, but yeah,
Mm,
you can actually directly give. For example, you can just take a path in the graph and say that, hey, I want to cover this path, and give it, let's
mm.
say, to another formal method and ask the formal tool to
Yeah,
generate
yeah,
an input.
that's another approach,
But
of
that is
course.
very expensive. But that is very expensive.
Okay,
So
got the point.
there are a lot of paths in the graph. And as soon as you give a
Right.
particular path to the tool, it is going to be very expensive for the tool to actually generate a instruction sequence specific to that path.
Okay, so that's why you are kind of doing it randomly, right?
Yes. So one method could be to improve the coverage, could be to use a random way at the start, and then later to shift to more targeted methods.
Yes, basically, I remember one of my work at Chess 2015, probably, yeah. So there we had a similar kind of exploration problem because of our hardware Trojans. So each instance is very difficult to figure out, but there are like you can figure. I mean, you can find the test case for like inputs for a activation for a lot of Trojans quite easily, actually. So we were doing that using some kind of heuristics as we were doing also. But there are some special cases which are really difficult to trace. and for them we were using some kind of SAT solvers to figure that out. So I was just thinking when you were presenting that whether that gives you better coverage or not, that kind of an approach.
Yes, so actually putting this, it would kind of depend on the type of, on the level of security you would want in the processor. For something as which is just for normal user consumption, uh, running the higher level test would actually decrease your efficiency much more because right now, okay, you find the root cause of a particular vulnerability, but you are finding it so that tomorrow you can go and mitigate it. And in many
Mhm.
instances, what is going to happen is this mitigation is going to affect your efficiency. Your efficiency is going to take a hit. So it's again a trade-off between the amount of security you want, the amount of efficiency, and also the amount of time you are okay with spending for detecting and securing your processor.
That's true, but like if your goal is to find out some vulnerability which can cause a lot of issues, then I mean
Mhm.
as a security engineer, people are more picky actually. They go inside and try to figure out
Yes,
everything. I mean,
yes.
that's how people go in this area. And finally, another question is that when you are like simulating the RTL and everything, are you also emulating the memory, the cache hierarchy, and everything? I think that memory is not possible, right? The cache hierarchy you might be doing, right?
Yeah, the memory is not possible. We are doing the cache hierarchy. Initially, we sort of randomize the data which is present so that we can get a better sort of coverage and a better idea about what all vulnerabilities we can find.
Mhm. Okay, thank you. That's all from my side.
Thank you.
Hi, I'm trying to understand the effect of compressed instructions over here. Can you tell
Mhm.
me if the coverage statistics change at all if you disable compressed in the CVA6?
We did not try disabling compressed instruction in the CVS6 to get an idea about the coverage statistics, but the vulnerability was not focused only on the coverage instruction. We also found it on the normal move instruction as well, like the non-compressed move instruction as well.
Right, but would I be correct to understand that the high achieved coverage in the iCache is because of compressed being enabled? Or this is for Boom. Can you show the statistics for CVA6?
I would have to go to the paper. But actually, we did not try for disabling the compressed instructions within CVA6. So even the paper would not have a statistic for comparing iCache coverage with and without compressed instructions.
Okay, okay, thanks.
Yeah, no problem. But I would say one thing. So the iCache, in case of the iCache, right, when it comes down to the compressed instructions, you would have a very small subset of paths which deal solely with the compressed instructions as compared to all the other instructions which are present within the processor.
Right, okay.
Hello.
Yes.
Yes. Hi, Pallavi. Thanks for the wonderful talk. I myself work in the area of network architecture security, so I have few questions regarding the security from what I understood. Can you go to slide 12?
Well, yes.
Okay. Yeah, I mean, I guess here you compared the existing detection approaches to your current approach, and you said how the other ones are not good enough and they have their own disadvantage. So, can you spell out what are the disadvantages? Because I'm new to this detection approaches, so just to highlight what are the disadvantages.
So, okay. So this is a very high level, this is a high, in this slide, we have a high level estimation of the approaches. So most of the approaches which use these methods actually suffer from these issues. Which particular one did you mention? The runtime detection?
Yeah, I mean formal verification and runtime.
So formal verification actually suffers quite a bit from the state exclusion problem and also some expert knowledge problems. So in formal verifications, there are quite a few papers which require you to use which require you to give the tool an input of the design which is manually written in some other language like a domain specific language and which is given as an input to that tool. And in many cases, it is not actually possible to automatically generate this input from the given RTL. But I would say the major problem of formal verification, as it is, as we also previously were discussing, is the issue of the state explosion and the efficiency problems that arise with it. When it comes down to runtime detection, actually, runtime detection is usually done on post-silicon processors. And when it comes down to post-silicon and you do detect any vulnerability, there is a drawback of the fact that there is not much you can do in fixing the vulnerability because it is already on the chip. So in some cases, you might have to, refabricate the chip, or even in some cases, it might be possible to get rid of the vulnerability, but to mitigate the vulnerability, but that is going to give you a lesser efficiency than if you were able to do it pre silicon.
Correct. Okay. So one other question was from me getting from what the talk was about. The detection are only for timing vulnerability, is it, or is it for other side channel detections also? Like let's say a
So
power side channel or a different kind of weight side channel.
this tool is only for timing side channels, but there are the methods you can sort of try to modify to work for the other side channel. But currently, it is only for timing.
All right. And yeah, you discussed about some novel vulnerability detections. This was one of the contributions of your work. So, could you spell out what are the novel vulnerabilities you detected?
So we detected 12 novel vulnerabilities, and out of those, eight were on CVA6. They were specific to the compressed instructions. So a lot of the compressed instructions on CVA6 as well as the move instruction suffers from the vulnerability of the timing difference when given a zero as an operand and a non-zero value. And there was also a timing channel in the again in the CVA6 processor, which was specific to the division instruction. We also found some known vulnerabilities in Doom and Rocket.
So for
And
CVS6, you found vulnerability in division instruction, right?
Yes.
But
Uh,
wasn't that
I
known? I mean, division instructions are usually timing dependent. That's kind of known thing, right?
yes, but in this case,
Unless you are doing parity reduction, it's always time dependent. So, I mean,
mm,
is it something that you are saying that it was not known for CVS6 that you have figured out?
yes, yes, it was not known for
Mm.
CVSX to do this that we figured out.
Okay, thank you.
Yeah.
okay, and just the last question about where you showed your overall solution architecture. There was a structure called mutator. Could you highlight what was the objective behind the mutator, or what was its work?
Oh, that's the operand mutator. You mean two, right? In this case.
Yes. Yes.
So the hardware fuzzer, right? It will generate your instruction sequences, but the timing vulnerabilities extract extract values from try to extract values like exploit the differences to extract values. So what you want is two instruction sequences which have the same instructions but have different values. So the hardware fuzzer will generate one instruction sequence, and the operand mutator will mutate all the values present in that instruction sequence, so that you are able to get multiple sequences which have differing values but the same instructions.
Okay, so you're trying to see whether some value takes a different path in the event run.
Yeah.
So just to connecting to this sentence, how are you measuring the execution time? It's just from RTL directly, or you have some special way of measuring execution time here?
So here in this case, what we wanted to go for was like a module level execution time. So we do get it from the RTL, and once we get it from the RTL, we go down to the module level and see how much time the module has been active.
So basically, if I'm getting it correctly, if you are simulating, getting the simulation time for a specific case, and then you are trying to see that which module caused that timing. Is it correct?
Yeah, yes.
Okay. And this fuzzer and operand mutator are commercial fuzzers and operand mutators, or these are also like something it has been developed somewhere
The
by some
fuzzer
people.
is the fuzzer is I it's an off-the-shelf fuzzer. On the other
Hmm.
hand, the operand mutator we developed ourselves.
Okay. Okay. Hmm. Thank you.
Thank you.
Yeah, Pallavi, one last question. So I think with your approach, you won't be able to detect any new microarchitectural channels, right? Am I correct?
Uh, what do you mean by microarchitectural
Yeah,
channels,
so
though?
timing channels created by some microarchitecture unit.
Like say prefetcher.
Yeah, anything, right? Let's say instruction cache. When you did this study, did you find any new timing channel which was not there before and you found it out?
In terms of the ALU channels that we found in CVSX, other than the division, those were novel. But
But those
so
those
as
were
long as
specific to execution units, right? So let's say if I go deep down to my especially the memory hierarchy, right? TLB, caches, prefetchers, buffers, whatever, right?
Mhm,
Did you
mhm.
find anything new which was not known to the community?
Not in those, but that is also in part because of the RISC-V processors not actually having that complicated of a
Hmm.
structure when it comes down to the TLBs. Basically, if you're able to uh, trigger the channel using your instruction sequences, then there is a chance that the tool would be able to find it. And I say chance because we are using hardware fuzzing, so it depends upon the seeds which are generated.
Okay.
Okay.
Yeah. Thanks again.
Okay, yeah.
Thank
Good
you.
evening. Hello. I'm just listening to all the questions and all. Thank you, Pallavi. Very nice presentation. I don't know much about hardware from the software angle. Can I say that this can be treated as a kind of VAPT, vulnerability analysis and penetration testing kind of thing, which we normally do for software programs? Hello.
Mm, yeah, I'm thinking about it. Yes, I suppose it could be treated as a VAPT,
Okay, then. So
but
normally,
I'm not very
yeah,
so
yeah, yeah.
I
Don't
have
worry.
very high level information about VAPT though, so.
Nice. I was just seeing some literature also when I was looking or listening to your presentation. So, how difficult it is to exploit these hardware-based vulnerabilities, or how easy it is to exploit?
It kind of depends upon the vulnerability. So one of the most popular ways of showing an exploitation of a vulnerability is by showing a cryptographic algorithm and which uses that particular instruction sequence, and then then just being able to exploit the crypto algorithm. But it depends. So if your vulnerability is using some specific module which the crypto algorithms don't generally use, then it becomes more difficult. You'll end up using some other algorithm. It depends upon the vulnerability that you found and how often that particular module that vulnerability is targeting is actually used.
Okay. I was just going through some basic information about this. They're saying that using this side channel attacks, particularly timing-based side channel attacks, it's very easy to leak the secrets like
Yes.
passwords, API keys, right? So
Yes.
have you done any kind of this thing, how these secrets can actually be leaked?
So with the detected vulnerabilities which we found in the work, we did not focus on exploiting them as such. But in general, yeah, there are various. So there will be like various courses which will actually go that route and show you, for example, the prime and probe vulnerability that I spoke about earlier in the presentation. That is actually shown in various courses in a practical scenario.
Okay, now this event graph extraction, which you said that you're doing so that it will be hardware language agnostic, right?
It is more that we will be able to find the locate the root cause of the vulnerability. So in case of similar to software, right? In when you're doing BAPT in the software, for example, if you found some vulnerability that is targeting the cross-site scripting, so you would try to find out the particular line within the code which is actually causing this attack to be possible. So
Okay.
similar to that, we wanted to find in the hardware which part of the code, the hardware code, is causing the
Yeah,
attack.
got it, got it. Okay, then thank you so much, and thanks everyone, and thanks Professor Panda for arranging this nice session. Thank you all.
Thank you. Thank you for inviting me to give a talk.
If there are no questions, we can wrap it up. Let me stop the recording. Okay, I have just stopped the recording. So see you all next month. Bye. Thanks.